Hello everyone. My name is Hitesh Poddar, and I'm a second year PhD student at NYU Wireless, working with Professor Ted Rappaport. Today, I'll talk about our work on NS3 implementation of sub-terahertz and millimeter wave drop-based NYU channel models, which we also call NYU Sim. Uh, Today in my talk, I'm going to touch upon a few of the use cases and applications of terahertz, followed by which I'll introduce what the NYU Sim channel model is and how does it differ from the channel modeling that we usually see in 3GPP. And then I'll introduce the NYU Sim 4.0 channel simulator, which we have built based on our channel measurements, radio propagation measurements that we have been doing over the past decade at NYU Wireless. And then followed by that, I'll talk about the NYU Sim implementation in NS3, which is based on the NYU Sim 4.0 implementation that we have in MATLAB. And then I'll talk about some of the results and conclusions from our work. So in 2019, for the first time ever, FCC opened up unlicensed spectrum in the frequency range of 95 gigahertz to 3 terahertz. And NYU Wireless was a big part of that conversation and the years preceding that big announcement. In the US, currently there are 4 unlicensed bands available above 100 gigahertz. Products are being made in these bands, not just for Wi-Fi, but to enable applications such as position location and sensing, and even other exciting applications. A lot of exciting opportunities exist in these bands as we have wide swaths of continuous bandwidths available. And as you can see on the table in the bottom right hand side of the screen, you'll see the currently the unlicensed bands which are officially given out by FCC to perform experiments. And these bands have a total continuous bandwidth of about 21.2 gigahertz. And one of the most common bands that researchers are looking at right now is the D band, which is centered around 140 gigahertz. And that is where I'll talk later in my slides, where NYU Wireless has recently been doing a lot of channel measurements, and we have built channel models in those bands. So sub-terahertz is officially, or basically in the research community, defined as the frequency range from 100 to 300 gigahertz. And in the sub-terahertz range, due to wider bandwidths, we get higher data rates and more spatial resolution, which enables us to envision applications and build products and services for things like extended reality, wireless cognition, spectroscopy, joint communications, and sensing. Now, in order to understand how the sub-terahertz band behaves, it is important that we create models to understand the propagation of radio waves in these bands. This slide, without going into details, just captures a high-level mathematical overview of how you can represent a channel impulse response, which is basically how your multipaths in the environment can be captured in a mathematical form for omnidirectional and directional antenna patterns. Now, to conceptually understand what is NYU model and how does it say differ from a typical 3GPP model. So one of the things that we had very early figured out and laid the foundations for is the channel modeling methodology that is used in the NYU models. So the NYU model employs a technique which is called the time cluster spatial lobe method. And this has been developed based on our observations from channel measurements that we have been conducting throughout the past few years. So in time cluster spatial lobe approach, what happens is we have a time cluster. The time cluster is basically defined as multipath components which travel close in time, but could arrive from different directions. And the other thing we have is something known as the spatial lobe, which basically indicates the main direction of arrival or departure of multipaths, where we do not care about each individual duration or delay of the multipath, but we look at over a particular spatial direction over several hundred nanoseconds, how many multipaths do we capture? So for example, if you look at the diagram below, you can see that in this diagram, all the yellow lines could indicate one spatial lobe. So that's one spatial direction. The green lines indicate another spatial lobe, which is another spatial direction. And there could be multiple multipaths in these spatial lobes. So for example, all the green lines could arrive over several hundred nanoseconds, but they are mostly coming from one particular spatial direction. So when you're looking at that direction, you could capture all the green paths. Whereas when you're looking at the yellow direction, then you would capture all the multipaths that come in that direction. Whereas if you try to understand the time cluster perspective. Then from a user point of view, the green and the yellow lines, which indicate multipaths from different spatial directions, they could arrive at the same time. Now, a better illustration of this, I'll show you in the next slide. So for example, if you see in this slide, here there are two figures. The left one indicates a omnidirectional power delay profile in time domain, which is created from all our directional measurements. So we take the directional measurements from our very precise horn antennas in channel sounding, and then we synthesize a omnidirectional PDP from it. And then on the right, you can see we have a omnidirectional power angular spectrum, which shows the distribution of multipath in space. And on the left figure, you can see that we have partitioned the PDP in two time clusters, and the small red dots, they indicate the multipaths which arrive from different spatial directions. And these red dots are plotted in the power angular spectrum on the right. The power angular spectrum is then also used to figure out the number of spatial lobes that can exist in the channel. And you can see that the number of time clusters, which is, for example, in this case, 2, and the number of spatial lobes, which again in this example is, say, for example, 2, depends on the thresholds that we usually choose when we create the channel models. And there are some physical intuition meanings. For example, to select the threshold for partitioning time cluster, we look at, for example, what is the typical distance between, say, two reflectors or scatterers in a particular environment. And then based on that, we compute the distance, and that distance is then used to separate these time clusters. And then for spatial lobes, we basically look at in the power angular spectrum, which multipath is the one with the strongest received power. And then from that, we can select a threshold of about 20 to 30 dB less than the peak, which is basically, for example, like the blue dotted line. And then everything above that gives us the spatial lobe. Now, once we have all these channel models that we have built using the time cluster spatial lobe approach, we put it in a simulator, which we call NYU Sim 4.0 simulator. So this particular simulator is a MATLAB-based simulator, which is free to download for both academia and industry. And NYU Sim 4.0 is the world's first channel simulator, which produces realistic wireless channels above 100 gigahertz based on measurements and models that we have built at NYU Wireless for all 3GPP listed scenarios. And it is free to use for both academia and industry and can be downloaded from the NYU Wireless website. It is currently open source, and it's an active project in development where we keep adding more and more scenarios. And as we go and measure higher reaches of the spectrum, we incorporate channel models in the simulator. We support drop-based and spatial consistency-based channel simulation for all scenarios. And this can be used to generate channel impulse response for a particular frequency range and bandwidth. As you can see on the GUI, there are different configurable parameters based on which people could obtain the channel impulse response and then use it for link level and system level simulations. Currently, the frequency range that we are supporting for NYU Sim is from 0.5 gigahertz to 150 gigahertz. And the bandwidth that we support is from the continuous wave signal all the way to 1 gigahertz. And if you see, we support all the 3GPP listed scenarios in NYU Sim 4.0. And I talk about NYU Sim 4.0 in particular because our NS3 implementation of NYU Sim model heavily relies on this implementation of NYU Sim that we have in MATLAB. So what we have done in NS3 implementation is we have taken this particular implementation in MATLAB and then integrated it into a network simulator. So that enables people to do all sort of like throughput analysis, packet drop analysis, understand the performance of channel model on these end-to-end network performance. I'll talk about these later as I go along. So this is one of the sample examples from NYU Sim MATLAB-based simulator. So that is the MATLAB-based NYU Sim simulator is mostly a graphical interactive simulator. So the channel impulse responses that you obtain, you can visualize it, for example, in this case, as I've shown here. So this is a particular case where we have run the channel at 142 gigahertz for a UMI non-line of sight scenario for a particular transmitter receiver separation of about 40 meters. So if you see in this particular example, NYU Sim in general gives you 6 sort of outputs, and this is for a drop-based simulation. So you can see that you get the angular spectrum, which shows you the distribution of multipaths in the spatial domain. You also get the time, the power delay profile in time domain for both omnidirectional and directional cases. You can also see the path loss and also see the multipath profiling over different antenna element, which becomes important for MIMO, where you're looking at different antenna elements. This is another sample example where we are running like a spatial consistency mode, which is basically when the users are in motion. How does the channel look like when a user is, say, moving along a particular trajectory? How is your angular spread of multipaths varying as the user is moving? How is your time domain power delay profile changing with respect to user movement? So these are also captured in the MATLAB-based simulator. And now I'll talk about how we use the same ideas that we have in the MATLAB-based simulator, and we implement this in NS3 for our users to be able to use these channel models to be able to do network simulations extensively in NS3 based on any of the millimeter wave modules or the 5G LINA module, which is there in NS3. So quick overview of NYU Sim. So if you look at the millimeter wave module in particular, the block diagram on the right shows how the millimeter wave module is currently structured in NS3. And the millimeter wave module was again built by researchers at University of Padua and NYU Wireless. And it is a very popular end-to-end full stack simulation module, which can be used to simulate end-to-end 5G millimeter wave networks. And currently it employs the 3GPP statistical model, which is based on 38.901 release 15. And the channel model that is available to use in this module, which is extensively used, is mostly the 3GPP model. But then in our prior work, we have figured out there are a few limitations to the 3GPP model. So for example, we have seen in our past work that 3GPP SCM for millimeter wave and above usually oversimplifies the actual wireless channel in outdoor scenarios. And we have seen that because of the simplification or the methodology used in modeling the channel in 3GPP, they do not match with what we observe usually in the field, which leads to a simplification. And therefore, when there is a simplified model, it leads to inaccurate system design or hardware design or system design. And the second problem that we have usually seen is the 3GPP models currently are limited to frequencies up till 100 gigahertz. So there is currently no channel model in 3GPP which extends beyond 100 gigahertz. And this is preventing researchers from studying or designing networks, for example, for the sub-terahertz. And because as engineers, once we are limited to frequencies below 100 gigahertz, there is no way we could design or study systems above 100 gigahertz. Thus, there is a very minimal understanding of the impact of the channel model on the end-to-end network performance. There is a quite a bit of study in understanding how the channel model impacts the physical layer in particular, but then there is no comprehensive study which exists on how these changes in channel model could impact your end-to-end performance, which in turn could lead to, say, different design of protocols and different ways of doing things. And because of this limited understanding of the impact of channel model, what we thought is NYU models, as it is based on real-world channel measurements, and as we show in our past work, that it is a bit more accurate compared to 3GPP models when it comes to especially millimeter wave and terahertz. It is imperative that to overcome these limitations and to understand the impact of these lower layer discrepancies, for example, how your channel model impacts, say, your SINRs, and then how does it translate to impacting your end-to-end throughputs, network performances. We implemented NYUSIM 4.0 in NS3, and under the hood, NYUSIM 4.0, which is in NS3, relies heavily upon the MATLAB implementation that we already have. So there are two different simulator components. One is the MATLAB based and the other one is the NS3 based. So now I'll just cover briefly upon how the module is structured in NS3 currently. So if you have ever worked with the 3GPP model in NS3, you will see that the diagram which I have here for the classes for implementation of NYUSIM in NS3, they are very similar to the 3GPP implementation. So we have a very similar analogy that we have followed from the 3GPP implementation in NS3 to keep things consistent, reuse most of the APIs wherever possible, and then extend the 3GPP model to also incorporate NYU models. But then again, we give the users the option to select the model. So one could select a 3GPP model or an NYU model, similar to how they would select any other model in NS3. So the major three components that we have in NS3 is the NYU channel condition model, which determines the line of sight or non-line of sight channel condition. Then the second one is the NYU propagation model, which basically models the large scale fading, which includes the path loss and shadowing. And these models, the large scale models, are again implemented based on the radio propagation data that we have collected at NYU Wireless, and the path loss exponents and shadowing that we have figured out from all these empirical measurement channel data that we have. The third component is the NYU spectrum propagation loss model, which computes the small scale fading, which again includes the fast fading and the frequency selective fading. And again, with small scale fading, the small scale fading parameters are again computed based on the measurement data that we have collected in different environments. However, what we have done is again to have or to reuse wherever possible the 3GPP implementation. We still use the 3GPP antenna area model. So that way, whatever is there in 3GPP, which defines how your antennas are, your placement, your antenna patterns, one could reuse that same antenna model in NS3 for NYU Sim. So you do not have to build a new antenna model for it because the antenna model is not different. So the line of sight probability model, which was basically the NYU channel condition model, as I said earlier, will help in statistically determining whether a particular device is in line of sight or non-line of sight from a particular base station or access point. And what we have observed in our past work is the 3GPP statistical models, especially the line of sight models for UMI and UMS scenarios, which is the urban microcell and urban macrocell scenarios. They are they are inaccurate, and that is because if we simulate the 3GPP line of sight models for UMI and UMS scenarios, you'll observe usually that the line of sight probability is still quite high for distances above 100 meters, which is typically not the case if we look at a real world UMI scenario. For example, measurements in Manhattan or New York City, when we conducted, we observed that line of sight beyond 100 meters drastically falls. And from those measurement data, we created our own probability models for UMI and UMS scenarios, which we call the NYU squared line of sight probability models. And for the RMS scenario, currently we do not have a line of sight probability model from our measurement data. We are on path to create these models. So for now, for the RMS scenario, we reuse the 3GPP models for line of sight that already exist. For the indoor scenario, we use the 5G CM based line of sight probability model because it is similar to the NYU squared model, and their measurement techniques very closely match with how NYU models line of sight based on channel measurements. Again, for INF scenario, we have recently finished our campaign of conducting measurements. And for now, we do not have a line of sight model. So what we have done is we have taken the average of all the 3GPP indoor factory line of sight probability models, and we have implemented that for now to determine the line of sight for indoor factory scenarios. But the takeaway from this slide is in the future, we expect to implement the line of sight models based on our own channel measurements for RMA, the indoor hotspot, and indoor factory scenarios. So for the large scale path loss models, basically this predicts the received power at a mobile device as a function of distance from the transmitter. And in NYU Sim, we use a closed-in free space reference distance path loss model with a 1 meter reference distance. And in our past work, we have found that the CI path loss model has superior accuracy and lesser sensitivity to error. And the CI path loss model can be mathematically expressed by this expression, which is shown here. In addition to this particular path loss, which basically the most important terms are the eta factor, which is the path loss exponent, which we determine based on our measurements, as I said earlier. Then we also have the shadow fading coefficient, which is again based on the measurements that we have conducted and figured out what the shadow fading deviations would be. In addition to that, in NYU Sim, we also give the option to NS3 users to implement atmospheric attenuation models, which is denoted by AT, the outdoor to indoor loss models, which is again created by NYU Wireless, and the foliage loss models, basically to study your penetration, say, through leaves to foliage. And these are again based on our measurements that we have conducted. So all the measurement data that we had, we incorporated them in this path loss model. And the terms like the atmospheric attenuation, outdoor to indoor loss, the foliage loss, the shadow fading, these are all optional. So depending on the use case, users can decide to enable or use these terms or prefer not to use them. But the mandatory terms are the free space path loss computation and the 10 eta log d factor, which is always there by default to compute the path loss that you could expect for a given distance. So this slide basically captures how we generate the small scale parameters in NYU Sim. So I will not go over the entire flow chart, but these are the steps, which is a bit similar to the 3GPP implementation, which captures how we generate these time clusters and spatial lobes in the simulator in NS3. And these are all mandatory parameters. And these are all implemented in a particular file similar to the 3GPP implementation. And if people have their own channel measurements, they could go and tweak these parameters. So these channel parameters are empirically determined after all the distribution and curve fittings that we do. And once we have these channel parameters set, we could generate the small scale fading on top of the large scale fading. And once we have the complete channel impulse response, which is a combination of your large scale parameters plus the small scale parameters, we could generate what is called as the channel matrix, which is then used for further simulations. So here, for example, we have captured the NYU Sim channel matrix implementation that we have in NS3. So if you see, this channel matrix is very similar to what we have in 3GPP. We did not want to deviate a lot from the 3GPP implementation. And this is because we wanted to keep things and reuse things mostly wherever it is possible to have a one-to-one understanding between 3GPP and the NYU models. The part where we usually differ is how we generate the parameters for the channel, but the channel matrix representation is not something which is different in NYU and 3GPP. Thus, we are using the same channel matrix implementation from 3GPP. However, what differs here is, for example, in the polarization matrix, the polarization coefficients, these usually come from the measurements that we have conducted in NYU wireless. Other than that, the antenna pattern, those spatial signatures, these have nothing to do in general with the channel measurements that we have conducted or the models that we have created. So wherever possible, we have reused as much as possible to keep a consistent design between 3GPP and NYU Sim. So this table basically captures in a very high level the different distributions that we have obtained from our channel modeling efforts based on channel measurements. And it captures basically what sort of distributions we use to generate the time clusters, the subpaths, the delays, the phases, the spatial lobes. And if you see, for all these scenarios that we have, basically for listed in 3GPP, we have the distributions defined for them. And we conducted measurements in different frequency bands over the past 10 years, which is from 28 all the way to 142 gigahertz. And these statistical distributions were already there in the MATLAB-based implementation. And now with this work, we have all these distributions in NS3 as well. And this is the channel parameters that are used in those distributions that I showed earlier. And this is for 28 gigahertz. And similarly, this is for 140 gigahertz. And currently what we do is for any arbitrary frequency between 28 to 140 gigahertz, we do a simple interpolation of these channel parameters. And mostly we have figured out from our channel measurements at other frequencies that the interpolation technique holds even when you compare it with the real channel measurements. And for simulation, just to see whether the implementation worked fine in NS3 for the NYU Sim model, we did 142 gigahertz path loss computation in NS3. And we figured out what the mean path loss is in line of sight and non-line of sight channel. And then we compared this with our MATLAB-based simulator, and these align pretty well, showing that the large-scale path loss model implementation in general is correct in NS3. Currently, we are also working on verifying the small-scale channel generations, and that is a work in progress, which we'll soon publish. And as of today, we do have a code base set up to release the current implementation that we have for drop-based models. But as I said, we are in the stage of verifying the small-scale models that we have also implemented. And thus, we expect somewhere around the end of July to have finally released the source code for people to sync, clone, and just use the channel model with any of the millimeter wave or 5G LINA modules to do these end-to-end network simulations. And finally, to conclude, channel modeling, as we all know, is very vital to understand radio propagation, especially in millimeter wave and sub-terahertz bands, where the channel becomes more challenging. And NYU Sim is based on real-world propagation data. About 2 terabytes of data were collected from 2012 to 23. And NYU Sim in both MATLAB and NS3 is an active open source project, which is free to download for both academia and industry. And the bigger plus point that we see is it allows researchers to use an alternate channel model other than the 3GPP SCM, and at the same time also allows researchers to simulate channels and design systems beyond 100 gigahertz for all 3GPP listed scenarios, which will enable and aid in the development of 6G as we envision. So thank you all. I would like to thank the industrial affiliates who sponsor our work at NYU Wireless. Thank you. I'm open for questions.
Thank you, Hitesh, for your presentation. So you have time. We have time for 1 or 2 questions now. Anyone wants to present a question? Okay, Tom has a question.
Yeah.
Maybe.
You can like it. Hi, could you clarify from your presentation? I believe that you said that the way that this works is it integrates a MATLAB-based channel model to NS3 at runtime. Am I understanding correctly that it's a MATLAB-based tool is consulted in the course of running the simulation? And if that's not the case, can you clarify what it is? And if it is the case, what are the performance implications of doing this?
Sure. So just to clarify, so we do not implement MATLAB under the hood. So these are the same things, but in 2 different packages. So NYU Sim in MATLAB is a separate software, and NYU Sim in NS3 is a complete re-implementation of the same MATLAB-based software. So we do not do a real-time MATLAB integration. Both are completely independent of each other.
Okay, so I also have just a very quick question. So I understand that these models were derived from experimental data. So is it easy or at all possible to access these these data sets that you used for generating these models?
Yes, so we do have some of our data that we have collected to create these models, which is currently available to basically the industrial affiliates who are there at NYU Wireless. Other than that, we also have some of the data sets that we have contributed, I guess, to NIST open source database. So for example, if you are looking at 28 gigahertz radio propagation data, I believe you can access it from the NIST repository where they host all the data sets from different universities for channel measurements.
Okay, thank you very much. So let's think again, Hitesh, for